I will wait for 2-3 minutes so that other participants will also join and then start this session.
Yes.
Okay. Okay, I'll start the today's problem solving session. I will share my screen. So this is the third week of the problem solving session. Uh, okay. Now, This week we'll try to solve the problems that are related to this uh, equation of motion for vibrations, which are under like damped and forced vibrations. So we'll try to see some of the examples, and also related to this response to the vibration under general periodic motion. Also, we'll try to solve one example, and also we can discuss if you have any doubts regarding this week's content. Okay. If you don't have any doubts like related to the contents, lecture contents, then we'll go with the problem solving. Okay, the first problem is like an automobile is traveling along a multi-span elevated roadway supported every 100 feet. So long-term creep has resulted in a 6-inch deflection at the middle of each span. The roadway profile can be approximated as sinusoidal with an amplitude of 3 inches and a period of 100 feet. So there is a bridge, and because of the creep, there is a midspan deflection of 6 inches. And we can model this kind of undulations using the sinusoidal wave, and the amplitude of the sinusoidal wave can be taken as 3 inches and a period of 100 feet. So now what they have done is there is one automobile which they have idealized as a single degree of freedom system for a first approximation study. And when fully loaded, the weight of the automobile is 4 kilopounds, and the stiffness of the automobile suspension system is 800 pounds per inch, and its viscous damping coefficient is such that the damping ratio of the system is 40%. So determine the amplitude ut naught of vertical motion ut of t when the automobile is traveling at 40 miles per hour. So in this case, what happens is we have a single degree of freedom system, and this is idealized as shown in this figure. It has got this spring as well as this dashboard, and when this automobile is moving on this undulated surface, there will be displacement that is being applied. There is a vertical displacement that is being applied on this support of this automobile, which will be transmitted to the mass. This problem is very similar to the um, displacement that will be transferred to the mass because of earthquake motions. Now we'll try to see how to write the equation of motion for this and solve these two parts. Now let's start with this idealization which they have given already. So we have some reference. So as this automobile is traveling over this, there will be a displacement, which let's call this displacement as UG. And the displacement of this mass M, let's call this as UT. This displacement UT is the total displacement with respect to this reference line. And there is one more displacement, which is the relative displacement between this support and then this mass, which is, we can denote this as U. Now, because of this displacement, this is disturbed, and we can draw the free body diagram for this mass M, and there is Ku and Cu dot. So these are the relative displacements, because only when there are relative displacements we are going to get this spring resistance as well as dashboard resistance. Now we can write the so these are the forces acting. So these are acting in the negative direction. So we have minus ku minus cu dot. This must be equal to the mass times acceleration as per Newton's second law of motion. So we have mut double dot. That is the total acceleration which we need to consider for the inertial force. Now, ut double dot. First, let us write down the equation for ut. Ut is equal to u plus ug. That is total displacement must be equal to displacement of this support plus the relative displacement between the mass and the support. So if we do the double differentiation, we will have u double dot t is equal to u double dot plus ug double dot. So we can substitute in this. We will have mu double dot plus ku plus cu dot is equal to minus mug double dot. So this is the displacement of this thing. So now this equation is very similar to the earthquake vibration response differential equation. Now let us write down the equation for ug. So that we can write down using this rod profile which can be approximated as sinusoid. So now ug is equal to 3 times sine. So they have given that period is 100 feet. So that means Tx is 100 feet. This is similar to the time period in terms of time, but here time period is like it is there in space terms. So we have 100 feet. Now that means omega will be equal to 2 pi by 100. So here we have 2 pi by 100 times x. Also they have given that the automobile is moving at a velocity of 40 miles per hour. So we can replace this x with vt. So in total we have ug is equal to 2 pi by 100 vt. Now let us just replace this 2 pi by 100 v with omega just for simplicity for ease of writing the equations. In the later when we have the final equation we can just substitute for omega as omega is equal to 2 pi by 100 v. Three sine omega t. So that means ug dot is equal to 3 omega cos omega t and ug double dot will be minus 3 omega square sine omega t. So let us substitute this in this equation. So we have mu double dot plus ku plus cu dot is equal to 3 omega square m sine omega t. So this is similar to the forced vibration condition with P naught is equal to 3 omega square m. So for this case, what is the steady state response that was derived in the lectures previously? So it was derived as we can write u of t is equal to P naught by k r d sine omega t minus phi. So at any point of time, if you have any doubts, like please unmute and ask your questions. So u of t is equal to P naught by k r d sine of omega t minus phi. So here P naught by k is equal to 3 omega square m by k. That is equal to 3 omega by omega n the whole square, because we can just replace k by m as omega n whole square. So, and this 3 we can just call it as ug naught, which is the amplitude of the displacement of the support of the automobile. Ug naught times omega by omega n the whole square. This is the p naught by k term. So this is just the relative displacement that we have obtained for now. But in the question, what is asked is the amplitude ut naught. That means we need to find the total displacement. So total displacement is a sum of relative displacement plus the support displacement. So we can just write that down. So the total displacement is summation of, at any time t, it is the summation of uh, ug omega by omega n the whole square times rd sine of omega t minus p plus this is ug naught. So let's write it like this.
Ma'am, I wanted to know how did you derive, how did you express P naught equal to 3 omega squared in that part of the research?
Okay, this part actually in the previous second week's course content, professor has derived the professor has presented the vibration when it is subjected to harmonic force, sinusoidal harmonic force. So in that case, you would have seen this equation, mu double dot plus ku plus cu dot is equal to p naught sine omega t. So I just compared this equation with the previous equation because we have already derived the solution for this equation.
All right, all right.
Yeah. So now we have ug naught, which is just 3. I'm just substituting with ug naught sine omega t. So now we have the total displacement as two sine terms. They're of same frequency, but there is a phase lag in them. And also the amplitudes are also different. So in this case, uh, there is a trigonometric identity which we can directly use to find the amplitude for this ut of t. So which is, so if we have two sinusoids, sine of k1 or else omega t plus theta 1, a1 and a2 sine of omega t plus theta 2. So the resultant of these two sinusoids will have an amplitude of a1 square plus a2 square plus 2a1 a2 cos theta 1 minus theta 2. This is a standard result in trigonometry which we will just use for finding the amplitude of ut of t. Now let's substitute for a1 a2 and theta 1 minus theta 2. Square root of ug of t omega by omega n square rd the whole square plus ug naught the whole square plus 2 ug naught square omega by omega n the square. We have rd and we have cos theta 1 minus theta 2. Here theta 1 is omega t minus p and theta 2 is omega t. So we just have cos minus p. Cos minus p is nothing but cos p. So we need to write down the equation for cos p. So what is cos p? This equation is actually the steady state response for the sinusoid when the SD wave system is subjected for this sinusoid wave. So the original equation was, if you remember, it was is equal to u of t is equal to c sine omega t plus t cos omega t. So to write it in a simplified way, we have assumed that uh, cos phi is equal to c by square root of c square plus d square. So these are all derived in the previous contents. So I'm just writing down the expressions for these things directly. So if you do all the substitutions, then okay, let me write down the expressions for C and D. C is equal to 1 minus omega by omega in the whole square divided by the whole square plus 2 zeta omega by omega in the whole square. So this is the expression multiplied by P naught by K for C. And similarly, we also have an expression for D. Minus 2 zeta omega by omega n. So similar denominator, the same thing here also. So now if you substitute for cos phi, then you will get cos phi is equal to so you have to substitute for C and D, and then which you can do that by yourself. So we will get 1 minus omega by omega n the whole square divided by square root of this term plus 2 zeta omega by omega n the whole square. So now this can be written as 1 minus omega by omega n whole square. This is the displacement response factor RD. So now we can substitute for cos phi here. So ut0. So in every term we have common as ug naught. So we can take that term out. ug0 omega by omega n whole power 4 rd square plus 1 plus 2 omega by omega n whole square times rd 1 minus omega by omega n whole square, and then we have one more rd. So this is equal to, so let's bring this, okay, let's keep the term on the right hand side. So ug naught square root of omega by omega n whole power 4 rd square plus 1 plus 2 omega by omega n whole square and 1 minus omega by omega n whole squared and rd square. Okay, now we can make substitution for rd. Omega by omega n whole power 4 plus 2 omega by omega n whole squared minus 2 omega by omega n whole power 4, and we have rd square plus 1. So this is equal to u naught g square root of, so rd square will be, let's substitute here, whole power 4 plus 2. So we have 2 power 4 terms. So this would be 2 omega by omega n whole squared minus omega by omega n whole power 4. And okay, rd square would be 1 minus omega by omega n whole squared, this whole square plus 2 zeta omega by omega n whole square plus 1. So I'm just writing here ug naught square root of 2 omega by omega n whole square minus omega by omega n whole power 4. So we can expand this square term, then we will get plus omega by omega n whole power 4 minus 2 omega by omega n whole square plus 1 and plus 2 zeta omega by omega n whole square. And then in the denominator we have this term, or else this can just be called as rd square. So here we have ug naught so here these terms get cancelled, and in the numerator we have only 1 plus 2 zeta omega by omega n whole square, and in the denominator this term 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square whole power 1 by 2. So that means the total displacement of the mass is ug naught times this factor. So if we take the ratio with respect to ug naught, then this is the factor that we get. So this is also called as the displacement transmissibility ratio for this problem. So this is the final equation that we have. Now let us substitute all the values in this equation. So if we go to the question, then we have, so they have given all the properties of this idealized SDOF system. They have given the stiffness, mass, as well as the damping ratio, which is 0.4. We need to find out. So in this, we need to find out omega by omega n. So omega n is equal to square root of k by m. So k is given as 800 pounds per inch, and weight is given as 4000 kips. So we need to convert that into mass. Square root of 800 multiplied by 4 kips means 4000 pounds. 4000 divided by g, which is 386. So it will go up 386. So what is the omega n that you're getting? Could you tell me? Can you calculate and tell me what is the omega n? So are you able to understand this derivation? So actually this is given as a standard result in the textbook, just to make you understand how it was obtained. Uh, so I have derived the complete thing. So for the problems, we can just directly use this formula. So that means when the support is undergoing a displacement of amplitude of UG naught, then the transmissibility ratio is this term. Yes, right. 8.78 radians per second. Similarly, we need to find out omega. We have substituted for 2 pi by 100 V. Omega is 2 pi by 100 V. So let's find out. V is given as 40 miles per second. We need to convert that into inch per second. So the conversion factor is 1.46. So what would you get? We need to convert that into feet per second because the length is in feet. So the conversion factor is 1.46. So what is omega? So I'm getting a value of 3.67 radians per second. And zeta is given as 40%, which means 0.4. We need to express it as a ratio. So let's substitute in the formula. So UG naught is amplitude, which is 3 inches. So that means amplitude, the total amplitude of the mass is equal to 3 times 1 plus 2 zeta is 0.4 and omega by omega n. Let's find out the omega by omega n ratio. 3.67 divided by 8.78. So 0.418. So 0.418 the whole square. So the square is for the whole thing, not just for this omega by omega n. So divided by 1 minus 0.418 square, the whole square, plus again the same thing, 0.4 multiplied by 0.418 the whole square, whole power 1 by 2. So could you calculate this value and tell me how much you got? Are you trying to calculate this? So this term would be 1.185 and the total displacement would be 3.56 inches. So this is the first part of the question.
Mom, zeta was given.
Sorry,
Question.
which thing?
Zeta.
Zeta?
Point four.
Yes, yes.
Damping.
Yes, it is given as 40 percentage. The damping
Oh.
ratio is 40 percentage.
Okay.
Okay, let's move to the second part of the question if you don't have any doubts. Okay. The speed of the vehicle that would produce a resonant condition for the total displacement. So we need to find out the speed. That means uh, this omega, the forcing frequency, is dependent on the speed. So first of all, we need to find out this forcing frequency where the resonance condition is occurring for this, the total displacement. So the resonance condition occurs when the amplitude is maximum. So the amplitude would be maximum when this ratio term is maximum, right? So this transmissibility ratio must be maximum, or else we can also say that when this squared of this term is maximum, the at same frequency ratio TR also will be maximum. So, and we can also substitute for omega by omega n term just for simplicity. So let's replace omega by omega n is equal to beta. Let's call it as beta. So then we will have TR square is equal to 2 zeta. So zeta also we already know. We can just directly substitute this. So 2 zeta would be 0.8 and then 0.8 square would be 0.64. 0.64 beta square divided by 1 minus beta square the whole square plus 0.64 beta square. So let's evaluate this term. 1 plus 0.64 beta square. So 1 plus beta power 4 minus 2 beta square plus 0.64 beta square is equal to 1 plus 0.64 beta square divided by beta power 4 minus 2 minus 0.64 would be 1.36 beta square plus 1. So to obtain a maximum, we need to uh, differentiate this TR square with respect to beta and equate it to 0. So let's do that. dTr square by d beta. This would be, so this is in the form of u by v. So for this, my 1 by v square. So since we'll be equating it to 0, we need not write that term. We will just focus on the numerator term, which is u prime v minus v prime u. So let's just focus on this numerator. So u prime is differentiation of this numerator. So that is 1.28 beta power 4 minus 1.36 beta square plus 1 minus v prime is 4 beta cube minus 1.36 times 2 would be 2.72 beta multiplied by 1 plus 0.64 beta square. This should be equal to 0. So let's just expand all these terms. 1.28 beta power 5 minus, please try to solve this equation and try to find the value of beta. 1.741 beta cube plus 1.28 beta minus 4 beta cube plus 2.72 beta and minus 2.56 beta power 5, so plus 1.741 beta cube equal to 0. So this term and this term gets cancelled. So we have minus 1.28 beta power 5. So actually for this case there is no standard equation, so we do have to do this derivation. So minus 1.28 beta power 5 and minus 4 beta cube plus 1.28 beta is equal to 0. So we can take beta common. So we will have 1.28 beta power 4 plus 4 beta square and plus 1.28 is equal to 0. So this is a quadratic equation in beta square. So we can write beta square is equal to minus 4 plus or minus square root of b square minus 4ac. By 2.56. So what is the value of beta square? So it must be a positive value. What is the value of beta? So you would obtain beta as 0.541. That means omega by omega n is equal to 0.541. So omega is 0.541 times. So omega n is 8.78. Omega n is 8.78. So that is 0.541 multiplied by 8.78. 4.75 radians per second. So, and we know the equation for omega, which is 2 pi by 100 times v. So we need to find out the velocity of the vehicle such that this condition is occurring. So we need to find out v. V is equal to 4.75 divided by 4.75 multiplied by 100. So you would get 75.59 feet per second. So this is the velocity of the vehicle when resonance would occur for UT. Are there any doubts in this question, in this problem one? Okay, then we'll go to problem 2. Find the displacement amplitude for the previous example if the vehicle is empty with a total weight of 3 kips. So previously the mass was given as 4 kips. Now the mass is changed to 3 kips. So for this mass, when mass is changed, they're asking us to recalculate the total displacement amplitude. So what are the things that would change when the mass changes? So basically the critical damping ratio would change and the natural frequency also would change because critical damping ratio is equal to 2 square root of km, and omega n, we know that it depends upon the stiffness and mass. So when the critical damping changes, the damping ratio also changes. So we need to find out these two things and then update the values in the transmissibility ratio equation. So that is what we need to do. So could you try to do this on your own? So please try to solve this on your own. So zeta 1 is 0.4 and zeta 1 is actually C by CCR. CCR1. So the C value, the damping of the system does not change. Since the critical damping of the system is changing, the damping ratio is changing. So similarly, we have zeta 2 is equal to C by CCR2. So using this relation, we can just do equation 1. Now we have equation 2 by equation 1. Zeta 2 by zeta 1 is equal to CCR1 by CCR2. So CCR is 2 square root of km. So that means we will have square root of m1 by m2. So now try to find out zeta 2 when only the vehicle is empty. So the ratio of masses will be same as the ratio of weights. So we can directly substitute. So that would be okay. Square root of 4 by 3. Yes, 0.461. Similarly, please find the updated value of natural frequency omega n prime k by m2. K is 800 kips per inch. Sorry, it's pounds per inch. M2 is 3000 by G, which is 386 pounds second square per inch. So I got a value of 10.14 radians per second. So now we have the values. Let's also compute the frequency ratio omega by omega n. So the initial omega was 3.67. 67 by 10.14. So that would be 0.362. So let's substitute in the transmissibility ratio equation for finding the displacement. One plus uh, 0.461 multiplied by 0.362 the whole square divided by 1 minus omega by omega n, which is 0.362 whole square plus 0.461 multiplied by 0.362 the whole square. Whole power 1 by 2. So UG naught is same again 3, and please find out this value. One plus 0.461 multiplied by 0.362 the whole square. 0.755 plus So we will get a total value of, okay, I will just check. 3.36. Let me check once again because I am getting a value of 3.85. Could you check your answer once again? Like, I got a value of 3.85. Okay, the answer is 3.85 inches. Okay. Please check your calculations once again. Are there any doubts so far? Okay, we'll go to the next example problem. A one-story reinforced concrete building has a roof mass of 500 kips per G and its natural frequency is 4 Hz. This building is excited by a vibration generator with two weights, each 50 pounds, rotating about a vertical axis at an eccentricity of 12 inches. When the vibration generator runs at the natural frequency of the building, the amplitude of roof acceleration is measured to be 0.02 g. Determine the damping of the structure. So they have given a one-story reinforced concrete building. So this thing can be approximated as a single degree of freedom system because most of the mass is concentrated at the roof, and this system has a natural frequency of 4 Hz. And this building they have excited using a vibration generator. So in the previous week's contents, the concept of vibration generator was discussed. So what is a vibration generator? There would be two masses. There are two masses of equal magnitude, m1 and m2. They would be rotating about a vertical axis. So when they are rotating in opposite directions, so like this. So this angle can be written as omega t. So because of this rotation, there will be a centripetal force, and the centripetal force is half m by r v square. So v again can be written as r omega. Here r is nothing but the eccentricity. So here we have half m by e omega the whole square. So this total centripetal force is half me omega square for each mass. And if you see carefully, then these things can be resolved into horizontal and the vertical components. So this angle and this angle are similar. These are alternate angles. So this is also omega t. So the component of this force in the horizontal direction would be, let's say this as P naught. So this would be P naught cos omega t, and this component is also P naught cos omega t. So these two components get cancelled out, and we will be left with P naught sin omega t. Here also P naught sin omega t. So the total force that would be generated by this uh, vibration generator is me omega square sin omega t. So this is the total force that is generated. Now in this they have given the mass, or they have given the weights and also eccentricity. So again, the response to this can be found out using the displacement response factors that we already found out. So, so in this case, P naught is me omega square. So let's find out this P naught value. So they have said that mass is, they did not give. So we need to find that out. It would be 50 by 386. And eccentricity is 12 inches. When the vibration generator runs at the natural frequency, that means the omega is equal to omega n, and omega n is given as 4 hertz. This is a cyclic frequency. This is actually not the angular frequency. So we need to convert this cyclic frequency, which is 4 cycles per second, into the angular frequency. So this is 4 multiplied by 2 pi radians per second. So this would be 4 multiplied by 2 pi. So this is 25.13 radians per second. So 25.13 whole square. So this is equal to 981.6. So P naught is 981.6. So determine the damping of the structure. They have to find the damping of the structure. What did they give? They gave that when the vibration generator runs at the natural frequency of the building, the amplitude of roof acceleration is measured to be 0.02 g. So they have given the acceleration response, not the displacement response. So we can write the acceleration response. So what is the equation for the acceleration response?
me omega square Ra divided by m capital.
Sorry.
Me multiplied by E into omega square Ra divided by m.
Okay, RD divided by M. Let me get that equation. So Ra is equal to omega by omega n the whole square times Rd, and the acceleration response itself, the acceleration amplitude is equal to P naught by m times Ra. Okay, I think this is what you have mentioned. Yeah. So, and omega by omega n is just 1. And we have me omega square, which is just P naught. M is the mass of this roof. Let's calculate this mass of the roof. M is equals to 500 into 10 cube divided by 386 kilotons. So we have 500 multiplied by 1000 divided by 386. So that is 1295.3 pound second square per inch. So, so let's substitute here P naught by M, and Rd is, we know, 1 by square root of 1 minus omega by omega n whole square, the whole square, plus 2 zeta omega by omega n whole square. So this term would simplify to 1 by 2 zeta, because this ratio, the frequency ratio, is equal to 1. So now this amplitude is given as, let's substitute for all the terms that we know. P naught is 981.6 divided by 1295.3 multiplied by 1 by 2 zeta is equal to 0.02 times G, which is 386 again. So that means the damping ratio would be 0.6, 1295.3 multiplied by 0.02 multiplied by 386. So what is the damping ratio of the system? 0.0491 zeta. Okay, this is a simple problem using the concept of acceleration response equation. Now let's see one more problem. So this is actually related to the accelerometer concept. So I thought this would be interesting to solve in the class, because accelerometers are widely used in practice, and maybe it would be interesting to know its principle and solve one problem. This accelerometer works on the principle which is very close to this uh, forced single degree of freedom system. In an accelerometer, there is a mass, spring, and damper components involved, and this accelerometer will be attached to the place where we want to measure the accelerations or the displacements. And because of this acceleration, it will be transmitted from the base to the mass, and it will be very similar to the, and this response would be very similar to the equation that we have obtained for sinusoidal response. If we assume that it is actually sinusoid, let's see what happens. So what I am saying is, in an accelerator, we have something like this. So we have this thing, and then there will be other sensing elements which convert this displacements or whatever is experienced by this STOF system. These things will be converted to the electrical signals which we will get as output, and these things are capable of recording only the relative displacement between this support and the mass. So that means we are able to record only the u term but not the total displacement, or this displacement which is being transmitted to this mass. So while measuring any kind of response, say for example accelerations or displacement, our goal is to actually measure how much this component is accelerating or undergoing, to which we have attached this uh, sensor. So we will see how this thing works. So for this we will go back to the response of SDOF system when base motion is applied. So u of t is equal to, so when it is actually subjected to the ground motion, what is the equation? So it's actually ug double dot rd times sine omega t minus phi. This is what we have seen just now, right? So this is the equation we have obtained when there is base displacement from the first problem as well. So this is the equation, right? So there would be P naught by K term. So okay, write this equation from the beginning. So we will have mu double dot plus ku plus cu dot is equal to minus mu g double dot. This is the acceleration of the base. So for this equation, the solution is u of t is equal to minus mug double dot by k rd sine of omega t minus phi. This is the response that we have. Now we want to measure this acceleration, but then what we are measuring is this displacement. So let's see the relation and understand few more things. So this can be written as minus RT divided by omega n square, because omega n is equal to k by m, that I just substituted. And this ug double dot, this is the amplitude of the acceleration of this thing, sine omega t minus phi. That means if you observe this equation, we are measuring the ug modified by a term RT by omega n square. That means the amplitude of this thing is getting modified by RT by omega n square. This omega n square term we would get to know through calibration, but this RT term, we know that it depends upon zeta and the frequency ratio omega by omega n. So while designing these accelerometers, what people do is they ensure that this RD term is not very much affected by this omega by omega n term. So to ensure this, there will be certain frequencies for which this can be ensured. So that we will get to understand when we solve this example. And also we are not measuring at time t, we are getting the response of this UG with a phase shift of phi. So that means the response that is measured by this accelerometer is both modified by a factor RD as well as it is shifted with a phase phi. So there will be a certain range for a given accelerometer during which this error is very less. So when RD is close to 1, and since we already know this omega n, then we can multiply this omega n square ut is equal to ug double dot sine omega t minus phi. So when RD is close to 1, at the time the error between the actual acceleration of the ground and the measured acceleration would be very close. Now let's see this example where base accelerations of different sinusoids has been applied. Base sinusoids has been applied, and then we will have to calculate what would be the error for different frequencies. So they have given the actual acceleration, and we know the actual measured, but the measured value would be RD times the actual one, RD times this value. So for measuring the error, we need to estimate this RD value. Are you able to understand what I'm trying to explain? You have any particular doubt in this?
And by accelerometer, do
Yeah.
we provide ground acceleration or it's a force we are providing in the system?
So
Are we
it is
providing ground acceleration or it is for the in force vibration we provide P naught sine omega t kind of force?
no, it is like the earthquake motions. So it will be transmitted from the base to the mass.
So it's a ground acceleration, ground force we are providing.
Yes, yes, yes. Yeah. Now we need to find out this uh, displacement response factor value for different frequency ratios. Now in this they have given that the natural frequency of an accelerometer. So for this omega n is equal to 50 hertz, and then they have also given the different frequencies for which we need to find out this thing. F1, let's consider 10 hertz, and the damping ratio for this accelerometer is also given. Theta is equal to 0.7, and okay, we have all the things that we want. So this is cyclic frequency, these two are in cyclic frequencies, so we can directly take the ratio. Omega by omega n would be 10 by 50, that would be 0.2. Now let's find out RD. RD is 1 by square root of 1 minus 0.2 squared the whole square plus 2 minus 0.7 multiplied by 0.2 the whole square. Square root of 1 minus 0.2 the square the whole square plus Yes. Yes, RD is very close to 1. So that means whatever is measured, let's call it as uh, UG measured double dot is equal to RD times the actual value. Let's call this as UG. So that means this is very close to 1. So to actually calculate the error can be calculated as actual acceleration minus measured acceleration divided by the actual acceleration. So this would be equal to UG double dot minus RD times UG double dot divided by measured. Sorry, we can take the ratio with respect to the actual UG double dot. That means error is equal to 1 minus RD. So for this case, for the first case, error is equal to 0. That means when the frequency ratio is very small, when it is close to 0, and also for this particular damping ratio, the RD value is equal to 1. That means the error is 0. So whatever acceleration is measured is very close to the actual one. So let's do the same thing for the next one. F2 is equal to 20 hertz. So for this case, what is the frequency ratio? Frequency ratio is 20 by 50. That would be 0.4. And then let's compute RD again. 0.4 squared, the whole square, plus multiplied by zero point 0.4, the whole square. So this time we would be getting some finite value. So this would be approximately 0.990, which means error will be 1 minus 0.990. That means 0.01 or 1%. And there is one more frequency for which we need to calculate the error. So I think I did not read the question. Let me go through the question. The natural frequency of an accelerometer is 50 Hz and its damping ratio is 70%. Compute the recorded acceleration as a function of time if the input acceleration is UG double dot T is equal to 0.1 G sine 2 pi ft for 10, 20 and 40 Hz. A comparison of the input and recorded accelerations was presented in the figure below. So we need to find the recorded acceleration as a function of time. That means we actually need to find this thing, which is this um, minus RD, this term. So which is given here. At the accelerometer is calibrated to read the input acceleration correctly at very low values of the frequency. So this actually means that they have found out this omega n square term. So now the output would be omega n square u of t. What would be the error in the measured amplitude at each of the given excitation frequencies? So we need to write the recorded acceleration as a function of time. So that we know the recorded acceleration would be omega n square u of t. So this is ug double naught t sine omega t minus phi. So for this, they have already given the equation. This is 0.1 g sine 2 pi ft minus phi, and we know the formula for phi. Phi is equal to tan inverse d by c, and that d by c expressions we already know. So now in the last part of the question, we have computed the error for two of the frequencies of the ground acceleration. Now we need to find out for the third one, which is 40 hertz. Rd is equal to 1 by, so let's find out the frequency ratio. Is equal to 40 by 50, which is 0.8, 1 minus 0.8 squared the whole squared, plus 2 multiplied by 0.7 multiplied 0.8 the whole square.
Point 0.85.
Yes. 0.85. That means error would be 1 minus 0.85, that is 0.15 or 15 percentage. That means 15 percentage is a very high error which is occurring at a frequency of 40 hertz. That means when the frequency ratio is close to 1, the error is higher. It's very high. So the same thing we can observe from these plots for which they have plotted. We can see that this is the actual one and this is the measured one, and there is a phase lag which is phi by omega, and this phase lag in terms of time is 0.005 seconds. This kind of phase lag is very small, and it can be ignored. And but if we see the amplitudes for the 40 hertz, we can clearly notice the amplitude differences. But for 20 hertz and 10 hertz, the amplitudes and the curves are very identical. So for this kind of accelerometer with this particular properties up to about 20 hertz, it gives very accurate measurements for the accelerations. Okay. This is about this accelerometers. I think there are actually different types of accelerometers, piezoelectric based and optical and so on. There are different types of accelerometers. Those things are classified based on the how this relative displacement is sensed. Yeah, this is something about the accelerometers. Are there any doubts like so far? Okay, let's go to the next problem. This is kind of a simple problem. So in this problem, a system is modeled by two vibrating masses M1 and M2 interconnected by a spring K and damper element C. For harmonic force F is equal to F naught sine omega t acting on mass M2, determine equation of motion in terms of the relative motion of the two masses u is equal to y2 minus y1 and the steady state solution of the relative motion. So here actually there are two masses which are interconnected using the spring and the dashboard. So if you see here we have y1 and y2, but however we need to write the equation of motion only in terms of the relative displacement between these two masses. So let's try to solve this problem. So we can solve this by first drawing the uh, free body diagrams for the two masses m1 and m2. M1 and M2. So, so on this thing, there is an external force F naught sine omega t, and because of this external force, it got disturbed, and there will be restoring force K times U and also K times U dot. So how is this U? U is equal to y2 minus y1. Let's say that mass m1 is undergoing a arbitrary displacement of y2 and mass m2 is going an arbitrary displacement of y1 in this direction. That means how much is the total deformation that the spring will undergo? It will undergo y2 minus y1. So that is the total deformation. That is why the restoring force would be in terms of k times y2 minus y1, which is just ku. And similarly, the relative velocity should be considered, which will be cu dot. And also the same restoring forces would be acting on this mass as well. Mass m1, which is ku and cu dot. Now for these two masses, let's first write down the equations of motion separately. For mass m2, we can write down m2 y2 double dot, that is the total acceleration which we must consider, plus ku plus cu dot is equal to f naught sine omega t. For the second mass, it will be, so these things are in the acting in the same direction as the positive convention for the displacement. So we can write down ku plus cu dot. This must be equal to the m1 y1 double dot. This is the unbalanced force. So now we have m1 y1 double dot minus ku minus cu dot is equal to 0. Let's call this as equation 1 and this as equation 2. Now let's multiply equation 1 with m1 and equation 2 with m2. m1 m2 y2 double dot plus m1 ku plus m1 cu dot is equal to m1 f naught sine omega t, and also the equation 2 will become m1 m2 y1 double dot plus m2 ku, sorry, minus m2 ku minus m2 cu dot is equal to 0. Now let's subtract equation 3, equation 4 from equation 3. So that would become m1 m2 y2 double dot minus y1 double dot plus m1 plus m2 times ku plus m1 plus m2 times cu dot is equal to, we have m1 f naught sine omega t. Now we can just divide the whole equation with m1 plus m2, and also this thing y2 double dot minus y1 double dot, this is nothing but the relative acceleration of these two masses, which is u double dot. We can replace this term with u double dot. So we have m1 m2 by m1 plus m2 u double dot plus ku plus cu dot is equal to m1 by m1 plus m2 f naught sine omega t. Now in this thing we can call this term as equivalent mass of this two mass system, where we can replace m is equal to m1 m2 by m1 plus m2. Now we have the total equation mu double dot plus ku plus cu dot is equal to m1 by m1 plus m2 f naught sine omega t. So this equation is similar to the equation of the forced vibration equation. So this is the equation of motion, so which is the first part of the question. So they have asked us equation of motion in terms of the relative motion of the two masses y2 minus y1, which is u, that we have got. The second part is the steady state solution of the relative motion. So this thing is very similar to the forced vibration, for which we know the solution already, and they're asking the steady state solution. So the steady state solution u of t is equal to p naught by k rd sine of omega t minus phi. In this, so p naught by k term would be, so here p naught is m1 by m1 plus m2 f naught. So and k is just k. So we have m1 by m1 plus m2 f naught rd by k sine of omega t minus phi. So in this we know the equation for phi. Phi is equal to tan inverse d by c, and d is nothing but tan inverse of d is what? D is 2 zeta omega by omega n the whole squared, and this term is, there is no square here, and c is 1 minus omega by omega n the whole squared. So the denominator terms will get cancelled because they are same. So this is the total equation of motion, the steady state solution for the relative motion. So this is the solution for this problem. Next, we'll just solve one last problem which is related to the solution for the general periodic uh, periodic excitation. So periodic excitation would be like In this third week's content, our professor has already taught the solution for the periodic excitation. So any kind of periodic force, it could be decomposed into infinite number of um, sinusoids and cosines. So using the Fourier series formula. So for solving this problem, we will use the same principle. So once we have the Fourier components for the force, we can substitute in the response equation. Now, let's see this question. So, determine the first three terms of the Fourier series expansion for the time varying force shown in the figure. So, this is the figure. So, this is actually, you can see that for a time period of t from 0 to t, it has two piecewise constant graphs. One is between 0 to t by 2. It is just constant with a positive amplitude of 30 kips. I think this is kips. And from t by 2 to t, it has a negative amplitude which is equal, but it is negative and 30 kips. Now, for this kind of periodic force, we need to find out the Fourier series expansion, and in particular, they're asking us to find the first three terms. So, this any force P of t can be written as A naught plus sigma j is equal to 1 to infinity Aj cos j omega naught t, sigma j is equal to 1 to infinity Bj sin of j omega naught t. So in this, we need to find out for j is equal to 1 to 3. So what is T naught? T naught is the, let's write down the equation, 1 by T naught integral 0 to T naught P of t dt. What is this thing? This is nothing but the average of this periodic function for a for one time period. That means the average of this thing from here to here. So this integral is nothing but the area of this curve and then divided by the total time period. For this particular thing, we can easily tell that this thing is 0 because this area and this area will get cancelled out. And let's try to find out the other terms. So, and Aj is equal to 2 by T naught integral 0 to T naught P of t cos j omega naught t dt. And what is the expression for Pt? P of t is equal to 30 for 0 less than or equal to t less than or equal to t naught by 2 and minus 30 when t naught by 2 is less than or equal to t less than or equal to t. So we need to break this integral down from between of into two components. So this would be 2 by t naught integral 0 to t naught by 2. So p of t for this case would be 30 cos j omega naught t dt and plus t naught by 2 to t minus 30 cos j omega naught t dt. Now let's evaluate this integral. So we have 2 by T naught. We can take 30 common from both these things. So we'll have 60. So integral of cos j omega naught t dt would be sine j omega naught t between the integrals 0 to t naught by 2, and then we have a constant 1 by j omega naught, and minus similarly 1 by j omega naught sine of j omega naught t multiplied by t naught by 2 to t naught. So this would be 60 by 2 by 2 by j. I'm just taking out j omega naught common and then substituting for omega naught, which is 2 pi by t naught. So that would become 2 pi j. So now we have sine of j omega naught t. That means sine of j 2 pi by t naught multiplied by t naught by 2. So we have sine pi j. J can take only integer values from 1. That means this component is just 0, 0, and then t is 0 means this term would be 0 minus. So similarly, here we already found out t naught by 2 would be 0, and if you substitute t naught, you would just get sine 2 pi j. That means 0 minus 0. That means these coefficients are 0. That means for all j is equal to 1 to infinity, the coefficients of cos j omega naught is 0. Now let's find out the coefficients for sine, which is bj. So bj is equal to 2 by t naught integral 0 to t naught p of t sine j omega naught t dt. So this thing, it would be 2 by t naught. Again, we have to break this down from 0 to t naught by 2, 30 sine j omega naught t dt plus integral t naught by 2 to t naught minus 30 sine of j omega naught t dt. So if you evaluate this integral 2 by t naught, again we can take 30 common, so that would be 60 by t naught, and here we have 1 by j omega naught minus cos j omega naught t between 0 to t naught by 2, and also minus 1 by j omega naught minus cos j omega naught t between t naught by 2 to t naught. So this is equal to 60 by t naught. So again, if you substitute, let me open that note again. So 60 by, we have 2 pi j again, minus cos j omega naught t at 0, this would be minus 1, and minus cos, we will get pi t, minus, since there is one more minus, we'll get plus cos pi t, cos pi j, because we have already substituted for t, so cos pi j, and then minus, so we will get cos of 2 pi j, and for all integrals this value would be 1. So here we have minus 1 plus cos, and this value is cos pi j. So we have 60 by 2 pi j. Okay, there is some mistake somewhere. So this is minus, okay, that you just brought out, minus 1 by j omega naught, and oh, so cos j 2 pi by t naught multiplied by t naught by 2. So 2 to 3. So we have cos j pi minus cos pi j, and then so here we have plus 1. So this is the whole thing, minus okay. So here we'll get minus 1 because there is one minus here, and cos j 2 pi by t naught multiplied by t naught would be cos 2 pi j. So that would be 1, but there is minus 1, so we'll get minus 1, and then again there is so minus cos, so again so we will get plus, because here the second term is minus and there is one more minus, so we will get plus cos pi j. So this is 60 by 2 pi j of 2 minus 2 times cos pi j. So this is equal to 60 by pi j 1 minus cos pi j. So this is the value of bj, the coefficient. Now we need to find out the expansion terms for j is equal to 1 comma 2 comma 3. So now let's substitute for j is equal to 1. So b1 is equal to 60 by pi, 1 minus cos pi is minus 1, so this would be 120 by pi, and b2 is equal to 60 by 2 pi, 1 minus 1, that is 0. That means for even values of j, this coefficient bj would be 0. So 60 by 3 pi multiplied by 2, that means 120 by 3 pi. So the three terms are, so p of t is equal to we will be left with only the two terms, which is 120 by pi sine j is 1 for this term, omega naught t plus 120 by 3 pi or 40 by 3 pi sine 3 omega naught t. So this is the solution uh, for the first part of the question. So this is the basic substitution for p of t for evaluating the Fourier series terms up to certain point. Are there any doubts in this? Okay, let's move on to the second part of this question. Determine the steady state response for the damped spring mass system that is acted upon by this forcing function. So this is the spring mass system that they have given. So for this system, when it is acted upon by this kind of periodic force, we need to find out the response. So in the lectures, for this kind of uh, excitation, the response is already derived. So we just have to substitute all the things which are given in the figure. So in this, the stiffness is given as 120 kips per inches. And zeta is 0.1 and weight is 128.66. So the solution, the steady state solution uh, consisting of infinite terms of sinusoids and cosines is obtained during the lecture. A naught by k plus, and we have the terms for consisting of aj and bj, but the terms involving aj I am not currently writing because we have just seen that aj coefficients are 0 for all j. So I will just write the coefficients of bj. So we have 1 by k integral j is equal to 1 to infinity bj 1 minus beta j square sine j omega naught t plus bj of 2 zeta beta j cos j omega naught t. So in this thing, beta j is nothing but the frequency ratio, which is omega, which is nothing but j omega naught divided by omega n. So we will just write down for the two terms that we got. So for that we already obtained the bj, and beta j can be obtained as okay. But anyhow, did they give the forcing? Okay, they have given that to be 30. Okay, t naught is nothing but 1 second. So from that we can find out omega naught. T naught is 1 second, which means omega naught is equal to 2 pi. And omega n is equal to square root of 120 by 128.66 multiplied by 386. So this will be equal to 18.97 radians per second. So let's find out beta 1. Beta 1 would be simply omega naught by omega n, that is 2 multiplied by pi divided by 18.97, 0.331, and similarly beta 3 would be 0.993. Zeta is given, so we know all the things. We just have to substitute, and this thing is 0. So we have u of t is equal to, so b1 is 120 by pi, that would be 38.19, and 1 minus 0.331 square sine omega naught is 2 pi, so that would be 2 pi t, plus 38.19, 2 times 0.1 multiplied by 0.331 multiplied by cos 2 pi t. This is for j is equal to 1. Let's also write for j is equal to 3. So that would be bj is 40 by 3 pi, 4.24 multiplied by 1 minus. So for this, beta j is equal to 3 times beta 1. That is, okay, we already calculated here. So 1 minus 0.993 square sine 3 times 2 pi, that would be 6 pi t, plus bj is 4.24 multiplied by 2 multiplied by zeta 0.993 cos 6 pi t. Let's just evaluate the terms. U of t is equal to 1 minus 0.331 the whole square multiplied by 38.19. So that would be 34 sine 2 pi t plus 38.19 multiplied by 0.1 multiplied by 0.331, that is 2.53 cos 2 pi t plus 4.24 multiplied by 1 minus 0.993 whole square, that is 0.059 sine 6 pi t plus 4.24 multiplied by 2 multiplied by 0.1 multiplied by 0.993. That means 0.842 cos 6 pi t. So as you can see, the coefficients for the higher frequency harmonics is much lesser than the initial lower frequency harmonics. I think when we write down the more higher order terms, we will note that these coefficients are much smaller. So which means that with few harmonics, we can approximate this periodic function and then find out its response. Yeah, that is the solution for this question. So are there any doubts so far? So if there are no doubts, maybe then we can close the session.